In this video, we will investigate two more properties of exponents. First, let's consider the number 0 used as an exponent. Looking at the equations shown on the slide, we can see that on the left-hand side, the exponent in each successive equation has been decreased by 1. So we move from 2 to the 4th power to 2 to the 3rd power to 2 to the 2nd power, etc. On the right-hand side of the equation, we can see that our answers get successively smaller, from 16 to 8 to 4, etc. More closely, we can actually see that each successive answer can be obtained by dividing the previous answer by 2. 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2. If we were to continue that pattern, we would reach the conclusion that 2 to the 0 is 2 divided by 2. In other words, 2 to the 0 power is 1. This fact might seem a bit counterintuitive, and you also might wonder if it's true regardless of the original base, that a number raised to the 0 power is equal to 1. So let's look at the following two equations. First, we have a to the 4th divided by a to the 4th equals a to the 0 power. This must be true because we know the quotient rule for exponents says that we can keep the same base and subtract the exponents 4 minus 4. The second equation says a to the 4th divided by a to the 4th equals 1. This also must be true, since in any fraction, if the numerator and denominator are the same, the value of the fraction is 1. Since a to the 0 and 1 are equal to the same fraction, they must be equal to each other. This gives us the definition of 0 as an exponent. If a itself is not equal to 0, then a to the 0 power equals 1. Let's look at one more property of exponents. This is called the power rule, and it applies when raising an exponential expression to another power. Let's look at the pattern shown on the slide. X to the 4th power is that base x multiplied by itself 4 times. N to the 4th power, similarly, would be n used as a factor 4 times. So if we have an exponential expression as our base, such as in the third equation, a squared to the 4th power should be a squared used as a factor 4 times. Now we can apply the product rule. Since all these bases a are the same, we can add 2 plus 2 plus 2 plus 2 to obtain the exponent of 8. And our answer is a to the 8th power. In the same way, y cubed to the 4th power would be y cubed times y cubed times y cubed times y cubed. And if we add the exponents, we obtain y to the 12th. Now looking at those problems and the answers, we can see that there's a shortcut we could apply showing a rule for raising a power to another power. To raise a power to a power, we simply multiply the exponents and leave the base unchanged. So a squared to the 4th power is a to the 2 times 4, or a to the 8th. Y cubed to the 4th power is y to the 3 times 4, or y to the 12th. The power rule can be expressed algebraically as a to the m power to the nth power equals a to the power of m times n. Now let's use these two properties to simplify some exponential expressions. In problem number 1, we have 7 to the 0 power. We've seen that any base to the power of 0 is equal to 1, so 7 to the 0 power is also equal to 1. In problem 2, we have 5x to the 0 power plus the quantity 5x to the 0 power. Now it's important to be careful of understanding what constitutes the base in each part of these exponential expressions, and following the order of operations, we apply the exponent first before we multiply. So in the first expression, 5x to the 0, the base is x, so we need to keep 5 times x to the 0, which is 1. For the second expression, however, the base is the whole quantity 5x. So the quantity 5x to the 0 is simply 1, just like anything to the power of 0 is 1. Now applying order of operations, we multiply 5 times 1 and then add 1, so we have 5 plus 1, or 6, for the value of this expression. Similarly, in problem 3, once again we have to be careful about understanding what the base is in each of these two expressions. In the first expression, negative 1 to the 0 power, the base is 1, and the negative sign is attached after the fact. So since 1 to the 0 power is 1, then we attach the negative sign, the first term in this expression has a value of negative 1. The second expression, however, the whole base is negative 1, and anything to the power of 0 is 1, so negative 1 to the power of 0 is 1. Now if we add negative 1 plus 1, we see that the value of this entire expression is 0. Problems 4, 5, and 6 require us to use the power rule. In problem 4, we have n to the 5th to the 4th, so we multiply the exponents to obtain n to the 20th. In problem 5, note that our first expression requires us to use the power rule and multiply 2 times 3 to obtain x to the 6th. Then we are multiplying that expression by x to the 9th, so now we go back to the product rule, keep the same base, and add the exponents. Our answer is x to the 15th. And finally, in problem 6, in the numerator, we would apply the power rule to obtain x to the 12th. And then since we're dividing by x to the 8th, we use the quotient rule to subtract the exponents and obtain the answer x to the 4th.